All right, so I guess we can get started for today. So last time on Wednesday we got started on the link layer protocols, or the data link layer. And so what we do today is we'll continue on that and try to finish off. These were the goals. We wanted to know the basic principles behind link layer services, and then we wanted to look at specific error detection, error correction. We want to look at how do we share a broadcast channel, and then addressing and local area networks. Last time we got started on the introduction and services. We also looked at error detection and correction. We got sort of started on multiple access protocols, so we will finish off that today. And then we will do some of the tutorial problems. We'll do tutorial 3A. Okay. And then next week we will take on LANs and addressing and ARP and so on. Okay. So just as a quick recap of what we did on Wednesday, we talked about some basic terminology. We said, when it comes to link layer, we will talk about devices. They can be end host or routers, as we'll call them nodes. And then the communication channel that connects any two nodes, we will call that a link. Right? And what the data link layer protocol does is it's basically responsible for transferring the data from one end of a link to the other end of a link. So basically it just takes care of one hop from one end to the other end. And then if it has to cross another hop, another link layer protocol will take over and transfer the data. So hop by hop. And the kind of things that a link layer may provide, it may provide things such as packetization, framing by adding headers and trailers on both sides of the packet. It may or may not provide reliable data services. So for example, wireless MAC protocols such as Wi-Fi will take care of reliability, but Ethernet and so on, they may not take care of reliability. And it's primarily driven by factors such as in a wireless network, errors are more common. However, in a wired network, errors are not that common, so we don't need to invest in reliability there. It may also provide you things such as flow control, error detection, error correction, and so on. Another thing we looked at on Wednesday was where is the link layer protocol implemented? And we saw that it's partly implemented in hardware in the network interface card or the network adapter card. And part of the link layer is implemented in software in the operating system itself. So that would execute on the main CPU. Okay? All right. And then we looked at error detection and error correction. So we looked at the basic format where we take the data packet. And if I want to provide error detection or error correction, I need to add some extra bits, some overhead associated with it. And I will transmit the data and those extra bits. And at the receiving side, I will get the received bits, maybe with or without error, and the error detection and correction code bits, maybe with or without error. But then I run some algorithm on it, and then based on that, I check whether there's an error or not. I make a decision. And last time we saw the use of parity codes, and we saw how a single dimension parity code would be useful for detecting if there's any error. And if you do parity in 2 dimensions, both the rows and the columns, then you would also be able to correct errors. A single bit error, but you would be able to correct it. Right. Then we moved on to MAC protocols or multiple access protocols. And in this case, the idea was that, of course, you can have 2 kinds of links. Ones which you don't share at all, it's a point-to-point link, or a broadcast channel like the Wi-Fi or Ethernet, the old traditional Ethernet, where you share the channel with many users. In this case, the multiple access protocol is responsible for figuring out what the rules are. And last time we looked at some of the desired properties which we might want in such a protocol. There were 2 main things. One is that if there is nobody using, if there's only one person using the channel, I should get the whole entire available resources. But if there are many people on the network, ideally everybody should get an equal share, 1 over. If there are m people on the network, everybody should get 1 over m. However, if the network is not very heavily used, only one user is active, let's say, we should not waste any of the network resources. that single user should be given all of network resources, right? And last time when we looked at one family of these protocols, which was channel partitioning, either it's time division multiple access or frequency division multiple access, we break our resources into smaller pieces and then give individual pieces to individual users. This is very good when all the users are active, everybody gets 1 over m. But if certain users are not active, then we waste those resources. So that was the drawback here. So now let's come to today's thing, which is about, let me turn off the light on top so maybe it will be visible better, 70. Yeah. So now let's come to today's thing, which is about random access protocols. Right? So what we want to do is, so previously the problem was, in this example such as here, user number 2, 4, and 5 were not active, right? But we had allocated slots to them, so these parts were not being utilized, so this was a waste. I don't want that. What I want is, I want to be able to utilize my resources fully. So in a typical random access protocol, then what we do is, assume a node has some data to send. When that node gets to send, it transmits at the full rate. It essentially occupies the entire frequency band and it transmits till it's done. Okay? You transmit at full rate. And here there was some, already the ordering was decided. User number 1, then user 2, user 3. There was a fixed assignment. Here also there's a fixed assignment of frequency bands to different users. But in a random access protocol, there is no fixed coordination. So I don't discuss with you beforehand that, I will transmit first, then you transmit. I do whatever I want to do on my own. I don't interact, I don't exchange, or I don't coordinate with anybody else. Right? We do what we want. So now the problem is that if I don't do any coordination with you, it is possible that you and I will both transmit at the same time. Cannot avoid that. Right? We are not, computers are not magicians or mind readers, so we really don't know when you will transmit if I'm not coordinating. And if that happens, we will end up with a collision. Right? And any random access protocol will have collisions. It's just a question of how much, and then how you deal with it. So what a random access protocol will then do is, it will specify a few things. It will first tell you what is the method we use to detect the collision. Right? How do we even know that there is a collision? And then, since now we have a collision, 2 nodes transmitted at the same time. It doesn't have to be 2, it could be 5 nodes transmitted at the same time. Now what do we do? How do we recover from this? So again, those rules will be specified by your protocol. And then there are many examples of such protocols, and the most celebrated ones are what we call Aloha. This was probably the earliest random access protocol implemented in a network. And back in the day, this was done somewhere in the US, in the islands of Hawaii. And then there was a specific version of that called slotted Aloha. So we'll talk about Aloha and slotted Aloha. These are not so much used anymore. There's still some used, but primarily what we use today are these protocols called CSMA, which stands for Carrier Sense Multiple Access, and then variations of that. Carrier Sense Multiple Access /CD stands for collision detection. This is basically Ethernet, and we will talk about this today. And then another version of Carrier Sense Multiple Access, but now we have CA instead of CD. CA is for collision avoidance. And this is what is used in wireless networks such as Wi-Fi. So CSMA CA is Wi-Fi, CSMA CD is Ethernet. Okay? So we'll look at these things today. We won't look at CA. I think Professor Tefek will take it up later on when he talks about wireless networks, but we will talk about just CSMA CD here today. Okay? But before we get into the CSMA part, let's start with the simpler protocols, which are Aloha and slotted Aloha. Okay? The history behind this is, again, 50 years ago, 40 years ago, people didn't have personal computers, and universities such as NUS would have one single big mainframe computer, right? And then the University of Hawaii, if you're familiar with Hawaii, there are 4 main islands, I think Oahu, Maui, the Big Island, and something, right? So the main campus is in the city of Honolulu, but then there are campuses of the University of Hawaii in the other islands. And of course, you won't have a cable connecting the islands, so they would have a wireless network. So students in the other campuses would use a wireless network to connect to the mainframe computer in Honolulu. But there are multiple campuses, and they're all trying to connect to the same computer in Honolulu. So they designed this Aloha protocol to determine who gets to transmit when. Right? And if you're familiar with Hawaii, Aloha is for hello, right? As well as goodbye for some reason, means both things. But anyway, so the whole thing started with simple Aloha actually, and then they improved it by doing slotted Aloha. But we will start with slotted Aloha anyway, because it's a bit easier to understand. Right? And previously, when we were talking about what are the desired properties of these protocols, we said that we don't want any synchronization. Right? It should not be that your clock and my clock is synchronized. That increases the complexity of things and so on. But this particular protocol requires synchronization. Okay? It requires, for example, time to be divided into slots of equal size. Right? So my clock time is there. My time is divided into slots of equal size like this. Let's say there are 3 computers, A, B, and C. They all want to transmit. One thing is they will all have to agree on the same time. Right? Their clocks are synchronized, which is tough, but have to be. And then this is time. Time is divided into slots of equal length. And in each time slot, you can transmit one packet and receive the acknowledgement for that packet. Okay? So within this is sufficient time for one packet plus ACK from the other side. So in this case, so previously I was saying, okay, the MAC protocol will specify 2 things. How do we detect a collision, and then what do we do when there is a collision? So how we detect a collision? I transmit a packet, I expect an acknowledgement back. Here everybody is transmitting to that central computer, right? If that guy doesn't reply back to me, I assume that there is a collision. I transmitted a packet. If somebody else also transmitted at the same time, there would be a collision and none of us would get an acknowledgement back. So we say, oh, this slot had a collision. If I get an acknowledgement back, good, I was successful. Okay, so time is divided into slots. All slots are of equal size, or frames are of equal size, and they all start at the same time. Now, any node can transmit, but we always have to begin our transmission at the beginning of the slot. I cannot say, oh, I'm going to transmit like this, right? This is not allowed. You cannot start transmitting in the middle of the slot. And then your transmission spans 2 slots. Not allowed. You only transmit at the beginning of the slot. And if in a situation like this, where 2 nodes transmitted in the same slot, like A and C, this is going to be a collision. Right? This will result in a collision. Only if a single node transmits in a slot, maybe something like this, this is successful, because only one node transmitted. Okay. So now let's look at the operation of the protocol. So this is sort of what I was drawing there. Time is divided into frames, all of are equal size, nodes are synchronized, and then you can only start transmitting at the beginning of the slot. So this is the operation of the protocol. Let's say this is the node. Time is going in slots, and right now I generated a packet. I can generate a packet at any time. It doesn't have to be at the beginning of the slot, right? So I may have generated this packet, and now it's the middle of the slot. So my transmitter will have to wait for the next slot to begin. I cannot transmit immediately. Wait for the next slot to begin, and then you can transmit. So the idea is, the application gives you a packet, wait for the next slot, transmit immediately. Don't have to care about what others are doing. Your application gave you a packet, as soon as the slot starts, send it. If you get an acknowledgement, good. No collision, you can move on to the next time slot, and if you still have more packets, you can send again. Okay. On the other hand, if there is a collision, that means you transmitted, you didn't get an acknowledgement. So you now know there's a collision. So now what do I do? Okay. So this is where the main part of Aloha comes in. It says, you wait for the next slot to come in. And now in this next slot, what would happen if you also transmit? Let me go back here. Right? Let me make this a little bit more. Okay. So let's say A transmitted in this slot. And let's say C also transmitted in this slot. So here we're going to have a collision, right? So now the idea is I should recover from this. So what are my options? I could say, all right, let's wait till the next slot, and I will retry again here. I could retry. A also says, oh, collision, let's wait for the next slot, retry. You're guaranteed to have a collision again. You could wait for the next slot and retry again. Guaranteed to have a collision. So it's a bad idea to retry in the next slot. But then if nobody retries, what will happen? It will be an empty slot. Right? Empty. That's not good either. You wasted the resources. So I should not have it should not be guaranteed that I will transmit, and it should not be guaranteed that I don't transmit either. So what we should do is we should choose probabilistically. Probabilistically. Right? We should introduce some randomness in here. And what the protocol says is, each one of them should generate a random number. Both of them. You generate a random number, I will also generate a random. A generates a random number, C also generates a random number. And we will put some threshold value, P. You can give it any number you want. There is a way of choosing this smartly, but just for the sake of it, let's say P is 0.3. Just as an example. So A generates a random number, C also generates a random number. And we see if your random number is less than P, then you get to transmit. Right? So you generate a random number. If your random number is less than p, you get to transmit. If it is more than p, you cannot transmit. If I had made this equal to 0.5, that's basically saying you toss a coin, a fair coin. If it's heads, you transmit. If it's tails, you don't transmit. Okay? So then what would happen? Let me maybe move here and show you through an example, since it's already drawn out here. Okay? So here is an example with 3 nodes in there. Okay? And let's take the example that in this case, all 3 of them have a packet to send. This is the first slot. They got a packet to send, they send immediately. So what's going to happen? A collision. Right? So now, each one of them is going to generate a random number. And let's say my P is 0.3. Okay? And let me put like this, node number 1, node number 2, node number 3. Just for the sake of an example, let's say A generated 0.45. Node 1 generated 0.45. This guy generated 0.73. This guy generated 0.81. All of them generated random numbers greater than 0.3. So what? Each one of them does this independently on their own. Node number 1 generated a random number, 0.45. Is it less than P? No. So this guy says, I will not transmit. Node number 2 generates its own random number. It has no idea what 1 and 3 are doing. It just checks its own number, 0.73. Less than P? No. You also don't transmit. Node 3 checks its random number, 0.81. Is it less than P? No. So you don't transmit. So in this case, we end up with an empty slot. Just our luck. Cannot do anything. Just our luck. So now, in the next slot, we will repeat the same process. So maybe this time, let's say 1 generates 0.17. Maybe this generates 0.01. Maybe this generates 0.66. So node 1 checks. Is my number less than P? Yes. So I would be transmitting. Node 2 checks. Am I less than P? Yes. This guy checks. Am I less than P? No. So in this case, 1 and 2 transmit. So what happens? Unfortunately, that's still a collision. It's a little bit better than before. Instead of 3 nodes transmitting together, only 2 transmitted together. But that doesn't help me. I still have a collision. So we have to keep repeating for the 3rd time. Right? Maybe in the 3rd time, this guy generates 0.9. Well, I wrote 8. So let's say 81. Let's say this guy generated 0.27. And let's say this guy generated 0. Some number, 71. So now node 1 doesn't transmit because it's more than P. Node 2 transmits because it's less than P. Node 3 doesn't transmit because it's more than P. So now only node 2 transmits. And this time we have a successful slot. Okay. And now the same process will keep on going. And if I just imagine that it's node 1 is done, node 2 is done, and only 1 and 3 are left, these 2 guys will keep generating random numbers, and depending upon what my luck is, Some will be empty, sometimes I'll end up with a collision, and hopefully at some point in time I will end up in situations where only one node transmits at a time. Okay. So in this particular example, I have some nodes with collision, some nodes are empty, some are successful. Any questions on the protocol? All right. Okay. So now let's look at what are the pros and cons, the positives and negatives of this protocol. The good thing is that when a node transmits, it can transmit at full rate. So which means that imagine a situation where there may be 3 nodes, 1, 2, and 3, but 2 and 3 don't have any packets to send. At the time, node 1 can keep transmitting at full rate, no problem. There won't be any collisions, and then it will be able to achieve the full bandwidth, no problem. Also, it's very, very decentralized. I can do whatever I want based on my local rules. I don't have to do any kind of coordination. Right? And the protocol was very simple. Just said if you have packets to send, wait for the start of a slot, and then you can send. And if there is a collision, next slot, just toss a coin, a biased coin, just generate a random number. If it is less than some value p, you can transmit. It's a very simple protocol. However, there's some disadvantages too. One thing is that it's a bit wasteful. Why? There are these empty slots once in a while where I didn't use my resources. Also, there are slots with collisions where I waste my resources. Right? So I can have collisions and idle slots where my network is not essentially used at all. Also, later on when we talk about carrier sensing, CSMA, we will see that here we have to wait till the end of the slot before we know whether our transmission was successful or not. Right? We have to wait for the acknowledgement to come back, and then we know whether we are successful. In some situations, we don't need to wait till the end. We should be able to figure out much earlier whether that's a collision or a successful. Okay? So this doesn't allow us to do that. And the other big requirement here was that we needed clock synchronization. Right? Everybody had to start at the same, everybody's time slot starts at the same point in time. If there are clock drifts, my slot starts here, your slot starts here, then we are in trouble. Right? So this puts more harder requirements on the clocks and the hardware. So now next thing you may ask is, okay, so how well does it perform? Right? But maybe before we get into that, so this was slotted Aloha. Right? There is another version of this which is unslotted Aloha, and that does not require any synchronization. In unslotted Aloha, which is also just called simply Aloha, what you do is, there is no time synchronization, there are no slots. You got a packet, send it out immediately. That's it. Don't have to wait for any time frame to begin or time slot to begin. You got a packet, you send it immediately. In this case, you are successful. After some time, you got another packet, you can send it out immediately. Let's say this is A, and let's say this is B. What if B got a packet to send here? The rule at B says, oh, I got a packet, I get to send immediately too. But now there's an overlap. So there will be a collision. Right? So what is the rule now? What can I do? There are many versions of this. One says, oh, you have a collision. So what you're going to do is you're going to wait for 1 packet transmission time. And at this point, you're going to generate. So wait for 1 packet time. Right? That's 1. And then generate a random NUM. Generate a random number. If less than, I guess I can just do, if less than P, then transmit. Else, wait. Else, let's say, go to 1. So essentially you go back here. You wait for 1 more slot, again repeat. 1 more time unit, and then repeat. Okay. So in this case, the good thing is that you don't have to synchronize your clocks. It's a little bit easier. Whenever you have a packet, you transmit. If you're successful, you're done. If you have a collision, you wait for a fixed amount of time, flip a coin, well, generate a random number. If it is less than some value P, you get to transmit again. Otherwise, wait for another unit of time, generate a random number, less than P, transmit. Okay. So this is unslotted or pure Aloha. So now that we have looked at these two versions of Aloha, now we are in a position to see which one performs how, right? How good these things are. So what we can do is we can say, what is the efficiency of these protocols? And the way I define efficiency is, let's say if I look at the slotted Aloha case, I can see, all right, if I observe for a long period of time, how many total slots were there? Of this total slots, how many were successful slots? The ones with a single transmission. Right? So what fraction of total slots are the successful slots? And I can define similarly for pure Aloha or unslotted Aloha. What fraction of the time was I spending sending successful packets? It turns out that for slotted Aloha, the best you can do is 0.37. That means at best 37% of your slots will be successful. That means 63% of your slots will either be wasted or they will have collisions. This is for a large number of nodes, not for 1, 2, or 3, but when n is pretty large. Okay? So when the network is big, means there are many users, at best you can get 37% utilization or efficiency, which is not really very good actually. Right? More than half of your time is wasted. And if you relax the requirement for clocks to be synchronized, that means I can transmit whenever I want, you pay a price. Price in terms of your efficiency. The efficiency of pure Aloha is half that of slotted Aloha. Okay. Your protocol becomes a little bit simpler, implementation becomes simpler, no need for clock synchronization, no need for slots to begin at the same time, but then it doesn't perform as well. There's more chances that there will be collisions with your packets. And as a result, your efficiency is half of that. Okay? In the 70s and so on, probably this was good enough. Right? And actually, it is also used today. Who uses it today? This guy. Your phone uses Aloha. Actually, it uses slotted Aloha in the beginning. So right now, for example, I'm not making any call. I'm not transferring any data. So the base station has not given me any resources. It has not given me any time slots, or it has not given me any frequency band to transmit on. I don't have anything. But if I want to make a call, I need that. I need a time slot, or I need a frequency band. So what should I do? So in a cell phone, in a cellular network, what happens is, maybe I think it's okay, we can spend some time. Right? This is how your typical cellular network works. So let's say Singtel has bought a certain frequency band. Right? So what Singtel does is it breaks up this frequency band into smaller subbands. Right? And the x-axis is time. It also breaks up time into frames. This is one frame, this is another frame, and so on. And within the frame, you would have time slots. Did I do 8? Anyway, you get the idea, right? So when I want to make a phone call, so let me draw this also. What the base station will do is, it will say, oh, you want to make a phone call? Here, I assign you this frequency band and this time slot. So every frame, that time slot is mine to send my data or my voice. Somebody else comes in, wants to make a call. The base station says, oh, I give this to you. Right? A third person comes in, and maybe they want to watch YouTube. They want to download more. They need a lot more than making a voice call. So in this case, the base station can also say, oh, I'm going to give these 4 to you. Just want to make sure I pick the same 4. Okay? So there's all this flexibility. But then how will I tell the base station that I'm going to make a call? How will I communicate with the base station? We don't know, right? This is after the base station knows I want to make a call. But how will I tell the base station? So what happens is, some part of this is set aside where different users can do aloha or slotted aloha. So nothing is assigned to anybody. Anybody can transmit in this particular slot. And then you send a request to the base station and say, I want to make a call. And then next time around, the base station will send you a special message saying, all right, I have allocated this red slot to you. So it keeps aside a bit of the resources where everybody can do slotted aloha. So if you want to make a call, I want to make a call, we are both going to use this time slot to send that request. And if we're unlucky, we will both be transmitting at the same time. Base station won't get anything. So then in the next time slot, we will again we'll generate a random number and then decide whether we want to go forward or not. Okay. So aloha and slotted aloha still have some use, but in these special cases. Questions? What's the typical length of a frame? This is usually in the order of a few tenths of milliseconds. Yeah. Any other questions? All right, so I digressed a bit, went into 4G or whatever, but that's okay. All right, so now coming back to aloha and slotted aloha, the problem here is that it's not very efficient, really. You lose quite a bit of your slots as either empty and then or with collisions. So then you think, how can I improve the performance? So if you want to improve the performance, the first step is you go back and see, okay, why was I doing badly in the first place, right? What was I doing wrong? And if you think about what we were doing wrong, or not, if not wrong, not very smart, let's say. What we were doing is we didn't care what anybody else is doing. I have a data to send. I feel entitled. I transmit. Don't care what others are doing. Right? Especially with the unslotted Aloha, for example, I get a packet. I don't care what anybody is doing. I just send it. Think about what we do in human conversation. If we are polite, if somebody else is speaking, we don't speak. We wait for them to finish, and then we speak. Right? So maybe we can do the same thing in a wireless or wired network, which means before I transmit, let me first listen. Is somebody else talking? Is somebody else using the channel? If they're already using, I should not do anything. Right? If you go back to my Aloha thing here, A was transmitting. Why does it? Okay. So if you look here, A was transmitting. The blue packet was being transmitted, and then the green node B got a packet at some point, and it immediately started transmitting. Instead, if it has listened to the channel and see if somebody else is transmitting, it could have stopped. And then it could have let A finish and then go. That would have saved collisions for both, right? We didn't do that. You have a packet, you can transmit. So that's the whole idea about CSMA, which says, all right, you may have a packet, but you don't transmit immediately. First listen to the channel and then transmit. So that's listening to the channel is what we call carrier sensing. This is the listening to the channel part. And multiple accesses, many users many nodes are transmitting on the channel. Okay? So the basic idea here is, if you have a packet, you should first listen to the channel. If the channel is idle, you can go ahead, fine. But if it is busy, that means somebody else is transmitting, you should wait, and then once they are done, then you can go ahead and transmit. That sounds very nice, right? Should solve all my collision problems. There shouldn't be any more collisions now. Turns out, yes, it helps to prevent most of the collisions, or quite a large number of collisions, but you still cannot avoid collisions completely. There will still be collisions. Then you must think, why? I sense the channel was idle. Then how come I will cause collisions? And the answer is propagation time. Imagine like this, right? There are these 4 devices, 4 nodes. They're all sharing a channel, which is a cable. Right? And time is going down in the y-axis, right? And let's say at some time t0, my node here decides it wants to transmit. It senses the channel. There is nobody. It can transmit. Right? Now it starts transmitting, and as a result, A is transmitting, so its signals will start going in this direction, and signals will also go in this direction. Right? And the yellow cone thing that I'm drawing there, it's basically showing the propagation. And as soon as it starts, the signal doesn't reach the end immediately, right? There's some propagation time involved. So it will take, that propagation time may be in the order of microseconds or whatever, but there will be a propagation time. Right? So your signal is propagating. Now imagine this time t1. At this time t1, my node here, the last one, gets a packet. So it says, oh, let me do carrier sensing. So D, let me call it D, this guy senses the channel at its end. That channel is still idle. Why? Because the signal hasn't propagated all the way till the end of the end of the cable yet. Right? The cable may be a few hundred meters long or a kilometer long. Your signal has only crossed engineering, hasn't reached medicine yet. And the node at medicine decides to transmit now. So when this node senses the channel is still idle. So it says, I'm allowed to transmit. I will start transmitting. But at some point, since both are transmitting, we will have a problem and there will be a collision. Right? And this is what is being shown. Now, the checkered pattern there is the part where signals from the two sources are overlapping. And this is the time the last guy transmits. This is the time over which the first guy transmits. And the first bit reaches here, the last bit reaches at this time, the first bit reaches here, the last bit reaches this time. So the point I wanted to make here is that even though you listen to the channel, and that will help you to avoid collisions, it's not going to get rid of collisions completely. There will still be collisions. And the reason is, signals will take some time to propagate. If I'm unlucky, I would sense the channel just immediately after somebody else has started transmitting. It's just that their signal has not reached me yet, but it's coming. And if I start right now, I will have a collision. Questions on this? Okay. Yeah. So if you look here, let's say when this guy was transmitting, right? Let's say the intended receiver was this guy. So the first bit came in. Here, there is no collision right now. You get the correct bit. These are all coming correct. But for this period of time, the two signals are mixed up. So these bits will be in error. And even if the last guy was also, let's say, sending to the same node as the receiver, these last bits will be received correctly. There is no overlap. But in the middle, there is an overlap between the two packets. And as a result, if you're using things like checksum or CRC or parity bits, you're going to fail. So it is not that every single bit is going to experience a collision, but some part of the packet will experience a collision. And that is enough to cause an error in your packet. Does that answer your question? Yeah. Other questions? All right. Okay. So this was the basic thing, right? And as with any other engineering problem, you come up with a solution, and then you say, okay, how can I improve this further? Right? So one way of improving this is that, imagine, let me erase these things. Let's take this last guy, node D that we had. When it sensed the channel was idle. Then it started transmitting. Fine. Till this amount of time, I hope you can see one red over the other. You cannot see one red over the other. Ink color. What should I take? Blue. For this period of time, you are transmitting, and the signal from this guy still had not reached you. But at this point in time, the signal from, let's say, B has reached D. Right? But what D is doing is it still continues to transmit, still continues to transmit, continues to transmit. Is it possible? And as a result, this entire duration, right, whatever was transmitted on the network, everything is a waste. Is it possible that I shut down transmitting unnecessary bits? The answer is yes, and that's the part when we add collision detection to the equation. And collision detection says this, right? So before I transmitted, I listened to the channel and I made sure nobody was active, and then I started transmitting. Collision detection says, fine, you have started transmitting, but at the same time, keep listening to the channel. If you find somebody else has started talking, then you stop. How do we do this in real life? In real life, how do I know somebody is using the channel? Let's say this is Ethernet. I don't want to pull my... Right? Let's say this is an Ethernet cable. How will my computer know that this is somebody is using this? It will basically measure what is the voltage level on this wire. Is it 0? Nobody. 5 volts, 3 volts, something? Somebody is using the channel. Okay? So let's say I sense the cable, 0 volts. So nobody is using it, so I can go ahead and transmit. So now when I'm transmitting, there will be something on this wire, right? How much? Maybe let's say between 0 and 5 volts it goes. But if somebody else transmits and their signal reaches, so occasionally my signal will go up 5 plus 5, 10 volts, more than the usual. And then I say, oh, collision. Okay? So while I transmit, I also measure what's the voltage level on the wire. And if it is more than what I expect, then I say collision. And that's the idea here. While you are transmitting, you keep listening, and all of a sudden if you see an abnormal rise in the power level or in the voltage level in the wire or in the channel, you say that there is a collision. And in this case, previously this device went on transmitting all the time, but now what would happen is, when I first sensed the channel, it was idle, so I can go ahead and I keep transmitting, still idle. But at this point, I realize that the voltage level has gone up. So then I don't need to transmit the rest of the packet. I know it's a waste anyway. So I stop. So you will see that the wasted part of the time where the channel was basically transmitting garbage, useless things, is much smaller than here. Okay? So by adding this collision detection part, we can improve our efficiency a little bit better by reducing the time that I waste when there is a collision. I abort my collisions quickly. I abort my transmissions during collision. Now, this collision detection is easy in a wired network. Why? Because, if the cable is this, a few hundred meters long, if you're transmitting 5 volts, on the other end, because of loss due to resistance and so on, maybe you get 4.8 volts there, still measurable. Right? But now imagine the antenna here. My laptop's antenna is here. When this guy is transmitting, maybe 200 milliwatts, something like that power level. But by the time in a wireless channel, the signal decays exponentially, right? 1 over r square, 1 over r to the 4, where r is the distance between the transmitter and receiver. Right? Let's say I'm here. When I transmit, my signal will decay very, very quickly. So let's say I'm the transmitter here. I'm transmitting. This is my transmit power. So I'm here. And there is an interferer somewhere far away, maybe here. And this guy transmits. And this is the interference power. This is usually very small that I really cannot distinguish. My own power will completely overwhelm the interference that is coming in. So it's not very easy to detect collisions in the wireless world. You can do it, but you need very, very sensitive equipment. If you need very, very sensitive equipment, expensive, lots of money. The cost of your phone or cost of your laptop will go up by a few $1,000s. So you cannot sell that. Well, you can sell that, but your market won't be as big. So in the interest of keeping things cheap, in the wireless world, we don't do collision detection. We do something else, which is collision avoidance. Essentially, we just try to avoid collision in the first place because it's so difficult to detect collisions. Okay? But in the wired networks, for example, in Ethernet, we will do collision detection. Okay. All right. So now that's all good. But one thing that we haven't talked about then is, all right, so now we first say, oh, there is a possibility of collision, all right, because of propagation delays. Then we said we can detect collision, so we can abort the transmission when if I detect a collision to improve my efficiency. But then either case, right, there is a collision. So how should I deal with it? How should I recover from that collision? So then that comes to Ethernet's collision, the recovery mechanism from collision. So this is how your Ethernet would usually work, or your CSMS-CD in the Ethernet protocol. Let's go through the steps anyway. So NIC is the network interface card, right, where the MAC protocol is implemented, or the network adapter card, if you want to put it that way. So when you get a packet from the network layer, you add your headers and trailers and whatever, and you create your frame. That's easy. And then we do CSMA. You sense if the channel is idle. If the channel is idle, you can transmit. If the channel is busy, you wait. Once the channel becomes idle, you can transmit. That's fine. Similarly, once you have started transmitting, you keep listening to the channel. If you don't detect a collision, you are done. And this is one interesting part here compared to what we were talking about earlier when we were talking reliability. There we say, send a packet, expect an acknowledgement. If you get an acknowledgement, you're good. If you don't get an acknowledgement, something bad happened. In Ethernet, there is no acknowledgement. You transmit, and at the same time, you detect if the signal level has gone up. So that would indicate a collision. If you detect that signal level didn't go up, everything was fine, you assume that packet has reached. You don't get an acknowledgement. The receiver will not send an acknowledgement. And the reason is, in a wired network, especially in the old days, even now in a copper cable, this is actually an Ethernet cable. Finally, I found something. Right? So there are hardly any errors. So we assume that if there is no collision, that means things must have gone okay. Even if I had put in an acknowledgement, what would happen is probably 99.999% of the time, everything is okay. You just keep getting acknowledgements. That's a waste of resources. You don't need, if most of the time the answer is yes, so you don't really need to say yes. Right? So in wired Ethernet, we don't do acknowledgements. All right. Now let's see, if you transmit the whole thing and there is no collision, you are done. On the other hand, now this is the interesting part here, right? If you detect another node was transmitting, so you detected a collision, what you do? You abort. Stop. And then there is this says you send a jam signal. That means you don't immediately stop. The protocol says you're supposed to send a few extra bytes, And that's a very small, finer detail, and it's just to make sure everybody else in the network, no matter how far away they may be, they will also be able to detect that there was a collision. Okay? We don't want to get into that. The whole idea is that, let's say, you detect a collision, stop. But now it comes to recovering from that collision. When will I get to transmit again? And this is the binary exponential backoff algorithm. That's where it kicks in. Right? So maybe what I do is I will draw it, and then we will be able to visualize. Let's say A and B. Let's say A transmits a packet, and at some point B also starts transmitting a packet, and then they detect a collision, and then they stop. Right? They stop. Now they have to do something. In Aloha, they just generated a random number, and then they decided. Right? Here what they do is, that's something similar. They will both pick a number, either 0 or 1. You pick a number. It's either 0 or it's 1. If it is 0, let's say you have picked 0, you get to transmit basically immediately. There is some standard time that you wait, a little bit of time, but basically you get to transmit immediately. So I will not draw this, I will just say you transmit immediately. If this guy also picks a 0, it also transmits immediately. And then you get a second collision. Problem. So what do I do now? This time, again you generate a random number, but in the range 0, 1, 2, 3. Hopefully this time you have picked different numbers. But let's say I pick 2, this guy also picked 2. Then what? Then it says you wait for some units of time. Right? So in this case, let's say 2 units of time is what I'm going to wait. What is this unit of time? The protocol says 1 unit of time is the 1 unit of time equals time to transmit 512 bits. What is the time to transmit 512 bits? Depends on which version of Ethernet you're using. If your Ethernet is 10 Mbps, then this is how much? 51.2 microseconds, right? Please correct me if I'm wrong. I don't have anything written. Anyway. If it is 100 Mbps Ethernet, is 5.12 microseconds. This 512 thing doesn't come out of magic. There's a reason behind it, even though we don't really care about it here. It has something to do with, So we say in an Ethernet, what happens in an Ethernet? You have a single cable and you have multiple nodes connected to the same cable, like in our example earlier, right? How long can this cable be? Can I have a single cable to connect the whole world? Maybe all of NUS, all of Singapore. There's a standard says the maximum length can be 2,500 meters. Actually, each segment is about 500 meters, but you can have repeaters in between. And the time to go, come back, the round trip time, plus, there will be some repeaters in between. You can have at most 4 repeaters. These are not related to the protocol, but just because I'm talking about it, I'm talking about it. I mean, these are part of the protocol, but too much extra detail maybe, but anyway, since we're talking about it. Including the processing time and the queuing and everything else here. This is roughly about, we want to keep it to some amount, some limited amount. So the designers said that 512 bits sounds like a good idea. Okay? So an Ethernet is at most 2,500 meters. In real life, it's actually less than 2,500 meters. So based on this maximum size, this dictates this 512 bits. It actually comes from there. I just thought that some of you might be curious where this 512 bit comes from. It comes basically dictated by the maximum size of the network and the time it takes for a signal to propagate all the way and then come back. Anyway, not important. What is important is I count my time units, 1 unit of time as the time to transmit 512 bits. So if my Ethernet operates at 10 Mbps, this is 51.2 microseconds. Okay? So in going back to my example, both the nodes picked the number 2. So this is going to wait for 51.2 microseconds, another 51.2 microseconds. And node B is also going to do the same. This is also going to wait for 51.2 and then another 51.2 microseconds. So it waited 2 slots. And then both will transmit their data. But again, collision, right? Because both are starting at the same time. Here I chose 0 or 1. Only 2 choices. So it's likely that we may pick the same number. And that's what happened by chance here. We both picked 0, so we had a collision. So next time, to avoid that, I double your choices. So hopefully this time there are 4 choices, so hopefully you'll pick 2 different numbers. But we were unlucky, we still chose 2 same number. So third time around, I double your choice. Now I tell, choose between 0 to 7. Right? And now let's be kind to them. Let's say this guy chooses 3, and let's say this guy chooses 6. So what is going to happen? This is going to wait 51.2, 51.2, another 51.2. Right? And then can transmit. And this time this is going to be successful, because this guy will keep waiting. Right? It has to wait for 6 of those units. Right? It will keep waiting. So every time you have and then after they are both successful, they can reset back to 0, 1. Next time they don't have to continue here. They can go back to 0, 1. Okay. So now, how long do I keep? So this is what we are basically doing is we are doubling the window every time there's a collision for the same packet. This is the exponential part of things, right? It's 2 to the power of something. But how long do I continue this? What it says is, you go from 01, 03, 07, 015. Right, so this is for the first collision, second collision, third one, fourth one, all the way up to 021023. And this will be for the 10th one. What if I'm so unlucky that even with the 10th time I retried, I still got a collision? Now it's 11 consecutive collisions in a row. Standard says stay there. No need to go beyond this, because that means most of the time you're just waiting anyway. Right? So then you say, okay, should I continue this forever? Usually what would happen is you'll go to the 16th, you're still at 1023, and then you still have a collision, just throw away the packet. And usually you won't try more than 16 times. You throw away the packet and then let whoever the upper layer is, let them deal with it. Question? All right. Okay. So this was the binary exponential backoff mechanism of CSMA CD. And this kind of an binary exponential backoff is also used in Wi-Fi when there's a collision. So the mechanism is very, very similar in the Wi-Fi case also. Okay, so far what we have done on Wednesday, we looked at partitioning algorithms, TDMA and FDMA. And today we looked at random access protocols, right, where we were taking turns. Random access protocols where there are no rules, no centralization of rules. You just do whatever you want to do. And then in case there's a collision, you deal with that collision somehow. Okay? So the last thing that we have here is the last family, or the third family here, is the taking turns MAC protocol. So before we get into this, let's talk a little bit about your partitioning base, such as TDMA, FDMA, and the random access. So they are both good for specific scenarios. TDMA and FDMA are very good when all the users are active. If everybody is active and you've given everybody a time slot in TDMA, everybody gets 1 over M. Right? So those are good when your network is active, everybody is active. But if you have a TDMA and only one person is active, then the remaining 5 slots in our example are wasted. Random access is the opposite. If you have only 1 or 2 users who are active, they can keep transmitting all the time, no collisions, everything is good, you get the full network bandwidth. But if everybody is active all the time, you're going to get more and more collisions. You'll end up with collisions more and more frequently. So random access protocols work well when the network is lightly loaded. You're not active. Well, only a few of the nodes are active. But as everybody starts sending data, network throughput goes down. You have more and more collisions then. So one is good for low loads, one is good for high loads. Now you say, oh, I want the best of both worlds, right? So then what do? You go to these taking turn protocols. Okay? And how does this taking turn protocol works? There are 2 options, common ones. The first one is called polling. Okay? And here you have one master node. This takes care of basically controlling the network. And then you have these devices or nodes, which we call the slaves. Right? And the idea is that the master would invite the slave. So you cannot transmit on your own. Only when the master tells you, that's when you get to transmit. Okay? So here the master sent a poll to the first node. The first node said, yeah, I have data to send, so you get to send. Then the master will poll the second node, or the third, it will go in sequence. Okay, so the idea is very simple. You have a master, and the master will go sequentially. First guy, do you have data? You can send. Next guy, you have data? You can send. Next person, you have data? You can send. And I keep repeating in a cycle. It's a fairly simple idea. But then there are some concerns here. So in this case, you can imagine if everybody has any data to send, you all will get your turn, and you'll all get 1 over m of the source. And if only this guy has data to send, this guy will send the data, and I'll quickly poll these guys. They will just say no, and I can quickly move on to the first node. Not as efficient as Aloha, let's say, but still not as bad as TDMA. Right? I still spend some time in polling. There's some polling overhead involved here. Right? So that's a con. That's a concern. I have to ask you, do you have data? Then you get to send. In Aloha, you could have sent directly. No need for any permission. TDMA, you could have sent directly. So there's, of course, this one, right? And there is some latency involved because imagine the scenario where only this guy has data to send. I poll, you send your data. Now these guys don't have any data to send. But I still have to go and ask, do you have something? No. Do you have something? No. Do you have something? No. Now I can go back to node number 1 again. Some latency involved, some delay involved here. And then imagine something happens to this guy, to the master. Maybe it reboots, maybe it hangs. Then the whole network is unoperational. Right? So this is what we call a single point of failure. Right? If the master goes down, the whole network goes down. In TDMA, FDMA, or Aloha, that's not the problem. If one node goes down, the others can still operate. Okay. So this was one. This is polling. And then the other protocol that we can have in terms of taking turns is, now we don't need a master anymore. Let's say I want to get rid of the master. So now what we can do is something called a token passing protocol. In this case, the network is usually organized in the form of a ring, right, a circle. And there is a special packet called the token. And when I initialize the network, I give the token to any one of them at random, let's say. And the idea is you can transmit only if you have the token. Only the node that currently has the token can transmit. Others cannot transmit. Okay? So what would happen is you have the token, you can transmit the data. Once you are done, you have to give the token to the next guy, just like what happened in the animation here. First, the token was with the node at the top. When the node is done with its transmission, it passes the token on to the next guy. If the next guy has data to send, it will send data. Otherwise, it will pass on the token to this guy. And in my example, the node at the bottom has data to send. So now it will send the data, and the data goes in a circle, right? So you send, the data circles back to you, then you know everything is done. Now you can release the token and give it to the next guy. Right. This is yet another version, and if you look at the polling-based protocol, are there any practical protocols that use this? Bluetooth. Bluetooth is based on polling. There's a master node and there are multiple slave nodes. Even when you pair with your friend, let's say, there's no master-slave relationship there, But one of your phones becomes the master, the other guy becomes the slave. Okay? And then this token passing based thing, it's also sometimes used, and historically it was mainly used in some optical fiber networks. Okay? Again, there are some overheads here. For example, you also have to transmit the token from one node to the other node. When you're transmitting the token, it's not data, so you're spending some of the time transmitting just tokens. Again, there is latency involved. Imagine, only this guy has data to send. The token still has to be sent here. This guy has to send the token here, and then you get to transmit. Okay? And again, what happens, let's say this is the node with the token right now, right? This is the node with the token. This guy decides to reboot or goes offline. Then the token is essentially lost. And nobody has the token anymore. So again, we can have a single point of failure if the token gets lost. All right, so this is sort of to summarize the different protocols. If I were to compare, channel partitioning works very well when all the users are active at high loads. Random access is very good in the sense that it's simple, it can be distributed, there is no need for any kind of coordination, everything is simple. But it tends to work well when the network is lightly loaded. If everybody becomes active all the time, then you have problems. Somewhere in the middle are the taking turn protocols, and they try to find the best of both worlds, but again they also have certain overheads and some drawbacks. Questions? Yeah.
What does it mean by dumb slave devices?
In the old days, what would happen is not all computers would have similar computing capabilities. Right? So, a dumb slave is more like it has fewer computational capabilities, but the dumb here is more coming from it's like you don't decide. The decision is with the master. You have to wait for the master to tell you that it's your turn. So essentially, you are not taking any decisions. You don't, quote unquote, you don't have any intelligence. You wait for the master. Master tells you, so you do. So it's dumb in that sense. But also, if you look from the technological point of view, usually, these would be like terminals with just a monitor and a keyboard. It would wait for a signal from the mainframe, and then you would transmit back. Yeah? Okay, good question. So the question is, when I get a token, I may have a queue of 50 packets. Do I get to transmit everything or just one? Usually just one. Otherwise, or some fixed limited number. You're not allowed to keep the token till you clear everything. What if you have a very, very big file? Then you're going to be unfair to the others. Right? You could hog the token, you could keep it to yourself for forever, basically. Right? Even if you don't keep, maybe I have, let's say, multimedia that I'm doing a phone call. You kept the token with you for 5 seconds. My voice call got interrupted for 5 seconds. That's not going to work for me. So it's usually just a single packet, but the system admin can say maybe 5 packets or some small amount of time. So, took longer than I expected, so maybe we'll skip the tutorial for today. Maybe we'll do it on Wednesday when we come back. It's already almost 5:30 on a Friday, so maybe we'll stop here for today, and then when we come back next Wednesday, we'll do tutorial 3A and also look at the rest of the things here.